All right, this is a recording of my final differential equations project. I'll be modeling the spring mass system of the Baja car suspension. Apologies for the weird recording method, but I realized that if I pressed record for screen record and then went into the presentation that you could only see the title slide, which is not ideal. So we're just going to run through the slides real quick here. So on the Baja team, we've got two different forms of shocks that we use. We use air shocks and we use conventional spring shocks. I noticed Tristan Hanley a few years back modeled our air shocks, and that led to some weird numbers because of air shock rebound. It's really nice for the actual use on the car, but it's very not nice for modeling. So I decided to go with our spring shock setup. And also the spring shock setup is what we're planning on going with next year, so it all worked out anyways. So took some measurements of the spring shock's equilibrium length and found the mass of our unsprung weight, so that when we went into the data collection, I'd have some useful figures there. Data collection wise, we basically just compressed the wheel center 3 inches and then dropped it from that platform and then recorded the position of the wheel center in slow motion as it oscillated over roughly a quarter of a second because the spring constant on our suspension components is quite high. So then moved into starting to look at how to actually model that data I had collected. So looked at the linear damp motion equations and then the root equations for the different damping conditions. I wrongly assumed initially that we wanted a critically damped setup. We actually want an underdamped setup for our car because it's more forgiving for bumps. So that was a condition that I had to look at later in the modeling. Excuse me. There's the data that I recorded. We just used the slow motion camera from the camp teams and recorded it there. Pretty standard. I said 0 is my equilibrium length. It seemed more logical what to do. Just basically took all my measurements and changed them by about 3 inches. So then I started looking at different damping conditions and then functions I found online from automobile setups. So actual car setups, which was a lot more useful than a lot of the other equations that I found for floating mass spring setups. Those were a lot less helpful. So then I took the underdamped equation setup that we wanted and then pulled it into the Desmos graphic calculator and then modified it over, I think, 12 different iterations, or maybe 13, and then arrived at this equation, which after putting in my rough initial conditions, ended up matching my data quite well. So you can see here that the losses experienced during motion, and then that it returned to 0 a lot faster than the equation, which makes sense when you consider the setup we have uses rubber components, which is causes a lot of friction. There's the model equation, put in all the data there. So sort of a numerical method to match, but frankly a lot of trial and error for modeling. Some sources of error, why the graphs don't match up perfectly. Data collection method was a little rudimentary. I wanted to use an accelerometer and a position sensor, but the code for that ended up being a lot more involved than I was able to put into it, but I'd like to do that in the future for data collection purposes anyways. Some losses during motion, kind of just bound to happen, and with how heavy our setup is, there's quite a bit of loss, and with how high our spring constant is. The rubber O-rings around the spring components also cause a lot of friction, so those losses you can see in the graph make a lot of sense. And then the mass used in the equation modification process was not entirely accurate because I was using the exact wheel mass added with estimates on the wheel centers and suspension components for the unsprung mass. So that won't be 100% accurate. And then some sources. This is where I found those helpful equations for modeling car suspension setups and then modified from there. Thank you.